In this video, we're looking at part 4 of the rates and equilibrium topic for GCSE AQA Chemistry. It's a dual and triple award topic, so all students taking this course will need to know what's in here. Going to recommend, as always, that you pause and try the activities as you go. In this video, we're going to focus on the effect of concentration and pressure. In previous videos, we've already looked at temperature and surface area. So we need to know how and why changing concentration of a solution will impact on the rate of reaction, and know how and why changing the pressure of a gas will impact on the rate of reaction. So let's begin with some general collision theory knowledge that you may already have. Have a go at these questions. So based on your current knowledge of collision theory, suggest what increasing pressure or concentration might do to a rate of reaction. Well, it will increase. If I increase the pressure, if I increase the concentration, it will increase the rate of reaction. But I'm going to add a little bit more to this. We spoke in the temperature topic about how an increase of 10 degrees Celsius doubles the rate. With concentration, with pressure, with surface area, it's much more straightforward. Doubling will double. If I double the pressure or I double the concentration, I double the rate. If I treble, I treble. If I halve, I halve. Using collision theory, how can we explain this? Well, let's consider that I double the number of particles in the same volume. That's essentially what's happening if I increase concentration or pressure. That will mean there will be twice as many collisions. And if there's twice as many collisions, there will be twice as many successful collisions. By successful collisions, what we mean is collisions where there is energy equal to or greater than the activation energy. The collision will result in a reaction. And that will mean that we're doubling the rate of reaction. So now let's look at a model that perhaps will help to explain this. Got a picture here of a shopping centre. It's a very busy shopping centre there at the moment. This is a shopping centre in Manchester. And you might consider going there on a late summer evening. Might be people outside in the sun, not very busy at all. And then you might go back again in the January sales. What will the experiences be like? In which of those scenarios are you most likely to bump into other people? And you would expect that to happen in winter at the January sales. If I've got multiple times more people, they're far more closely packed. They're more likely to bump into each other than if you've just got a few people wandering around on a late summer evening. So we could take this further forward and say that if I double the number of people walking around the shopping centre, then I might double the number of times people bump into each other. If I increase it by a factor of 10, I increase the number of bumps by a factor of 10. Now within that group of people, however many people are there, there will be a small proportion of people who would get very angry if somebody bumps into them. What do we think generally would be the case if we take an average sample of people and we've got a particular percentage of that group of people who might get angry if they're bumped into? What would happen if there were twice as many people and twice as many collisions? Well, there'd be twice as many reactions. There will be twice as many people getting angry when somebody bumps into them. And if we think about this in the model, what we're seeing here is the people are the particles. If you double or treble or quadruple the number of people, just like you double, treble or quadruple the number of particles, then you are doubling, trebling or quadrupling the number of collisions, and you are therefore doubling, trebling or quadrupling the number of successful collisions and therefore reactions. And that's why we get the impact on rate. Now there is a practical that goes with this. What do you predict will happen to the rate of reaction if I increase the concentration of hydrochloric acid? Well, we've spoken about this at length. Increasing concentration increases rate. We can take it further. Doubling concentration doubles the rate. Halving the concentration halves the rate. We can quantify it. Now let's look at what that practical may actually look like. Got a method there, you can pause and take a read through. We're reacting marble chips with hydrochloric acid, and we are measuring the volume of carbon dioxide gas given off. And we've got the method here which you will need to be familiar with. So we're using 1 gram of marble chips, measuring that in a weighing boat. We're setting up the apparatus as we can see. This is a good cross-sectional diagram. It's cross-sectional because the tube goes through. It's not broken by the bung. It's also fully labelled. And we're going to do this for 3 different concentrations of acid: 1 mole per decimetre cubed, 0.5 moles per decimetre cubed, and 0.25 moles per decimetre cubed. And we're going to measure the volume of gas, but we're not just going to measure how long it takes to get to a certain point. We're looking every 30 seconds for 10 minutes what the rate will be. We'll do it for 1 molar, and then we set the apparatus up again and do it for 0.5, and then we set the apparatus up again and we do it for 0.25. Now, what you may then have to do is plot those graphs. You'd need to pick a suitable scale. You'd need to make sure that the axes are labelled. And you can see here that what we've got is an extra challenge. This is something that was discussed in their very first video in this topic, how to work out the rate of a reaction at a given point in the reaction. And we do that by drawing a tangent to the curve. Now, I've not provided you with any data here, so I'm going to show you a sketch of the sort of graph that you might see here. So we have the graph paper, and I'm going to use colour, and I've got the colour-coded key here to show the 3 different concentrations: 1, 0.5, and 0.25. I've labelled my axes, time in seconds, and volume of gas in cm cubed, and then I'm going to sketch on what these might look like. So I would have points plotted and I draw my curve of best fit. We can straight away see that the rate of reaction is higher with 1 molar and lowest with 0.25 molar. But if we wanted to measure the actual rate of reaction at 0 seconds, we would need to draw a tangent to the line. And we draw a tangent to the curve by making sure it only touches the curve at that point, at 0. And I'm not going to go through the calculation here. As I say, we talk about it in the first video in this series. But to calculate the gradient, we look at the change in y over the change in x for each of the 3 lines. And we would see fastest rate of reaction, second fastest rate of reaction, and slowest rate of reaction in the 3 going across. Okay, couple more questions. What happens to initial rate of reaction? Remember, when we talk about initial rate of reaction, we mean at 0 seconds. As you increase concentration, it increases. And mathematically, is there a relationship? Well, we've spoken about this already more than once within this video. It's not just increasing increases, we can quantify it. Doubling rate doubling concentration doubles the rate of reaction. Halving halves, trebling trebles, etc. What were the control variables in this reaction and how could it be improved? Well, based on the method, there was only 1 control variable that was actually controlled, and that was the volume of acid. We used the same volume of acid each time. So that means there are other potential control variables that we have not done anything about. What might they be? Well, we didn't talk about temperature. We could try to maintain a constant temperature. At the very least, we could measure the temperature throughout the experiment so that we can see if it changes and decide if that would have an impact. But we could do something to ensure we're using the same surface area of marble chips, and that would help us to get results that we could have a greater faith in, an idea that they are valid. That takes us to the end of this video. Thank you for listening and goodbye.